Hello dear students, welcome back. We were discussing beams and we have one more important topic left in chapter 7 to discuss. Before we discuss that, obviously once again I hope that you are watching this from the safety of your homes and you are safe, you and your family are safe. Now please, I have already emailed you how the evaluation for this course will be taking place. Since the homeworks are going to be an important part of the evaluation, I strongly urge you to keep going through the material as I post it. If you have to binge watch it, you binge watch it, but you finish it. Do not wait till the end of everything to finish. I have not received too many complaints about this. I received a couple of emails about how things can be improved, but other than that, I have not received much. As I said, please feel free to give me feedback. Okay. So now today what we want to discuss is discuss the case where you have a beam which is simultaneously experiencing a shear force and bending moment. Okay. So today we will investigate the case where a beam simultaneously experiences a shear force and bending moment. Okay. Now, in the very general sense, where you have an arbitrary bending moment, an arbitrary shear stress, an arbitrary geometry, changing geometry, etc. The problem has to be solved via, let's say, one of the easiest ways is, or one of the most, method which is often preferred by researchers would be full three-dimensional solutions to the equations of elasticity. And those obviously would be becomes very complex, and there will not be any closed form solutions for very general cases. But here, if we make certain assumptions, we might be able to get certain answers for us. One of the foremost assumptions that we are going to make, okay, will be that the equation of where we discuss the flexure formula will remain valid even in this case. So remember, if I had to go back, so remember, when we are discussing this particular formula, flexure formula, we had made the explicit assumption that V was 0, and this was very important in the derivation of the result. So now we are saying that V is not 0, but we will override our the conditions that we had laid down for getting this result, and we will say that this formula, flexure formula, remains valid even in the case of a shear. Okay. So let us see what are the assumptions we need to make along the way. So one of the first assumptions we make is the flexure formula remains valid despite the presence of a shear force. Okay, now the next step is to draw a beam with a shear force and bending moment. I do not want to do that again because I think I have done it previously. Right here. Yes. Okay, so I will just take this. Okay, so this is our differential element dx along the length of the beam. This is x, this is y, and this is z. We have a shear force present, we have a bending moment present. Now I have labeled both as mb, but obviously to accommodate for the fact that there is a v, this mb will have to change, right? Because we know that dm by dx is equal to v with a negative sign. So within this differential length, this will be mb and this will be mb plus some other dmb. Okay, the d is the differential operator. We can have a similar variation for v, and one of the first things you want to notice is that, let's say you take an imagined box here. This is an imagined, and if I had to draw it here, let's say, right? So this is a differential volume, and I've just drawn that here, right over here. So according to our accepted notation or accepted convention, this V is going to create a shear stress, and we are going to name this particular component sigma xy, and this component is sigma yx. So x, because it points in the direction of x, if you remember. So now we also know that sigma yx has to be equal to sigma xy. This particular requirement is obvious to us because we have already discussed this before, but it gives rise to very interesting results in this particular case, which sometimes I feel they're almost non-intuitive in some sense. So see, if this volume is right at the top, okay, where this circle ends, exactly at the top, then this surface is being shared by the top surface. And what shear stress are you presenting there? Nothing. If there is no shear stress there, this should be 0, isn't it? So what will happen to this? It will also be 0. But V is there. Isn't that interesting? So by putting it here, this differential volume, you suddenly discover that this term has to be 0, which forces this other term to be 0, despite the fact that there is a shear stress. So at the top, the shear stress has to be 0. That is quite remarkable, isn't it? I mean, if you were naive, okay, a naive guess, a naive guess would say that my shear stress, I also end up trying to write tau sometimes, but we have been using sigma all along, and I'm just going to focus on that. And a naive guess would be that sigma xy is simply V by A being the area of this entire surface right here, and this happens to be incorrect. Okay. Interestingly, okay, we'll come back to this. Okay, so I'll come back to this particular point at a later stage. So we have realized that we cannot be using this kind of a simple guess, and that doesn't work in this particular case. and all this has to do with the fact that you now need to balance the shear stresses have to be equal, etc., etc. So what do we do now? Well, the easiest thing is to fall back on what we know best, which is force balance. Okay. Now to do force balance on this, what we will do is we will create, and I've already used many colors. Okay, let's see. Let's choose a color. Choose an order. Okay. So what we will do is we will take an area here, and we will say that this area is A1. By the way, I'm going by the notation in your book, so that is easy for you to understand. I mean, you could use other notations as well. And that this height here, this is my Y1. Okay. So now you do a force balance on this differential, on this particular area, whose size is on this face here, area is A1, and the other length is a differential element Tx. Okay, this is obviously exaggerated. Don't get me. This is I'm implying a very small area right here. Okay, so let's do a force balance then. Okay, let us do a force balance. So let us perform a force balance on this volume, and the only force balance that is interesting enough to perform is summation Fx. And what are the different forces here? Well, we have on the face on the right hand side, we have sigma xx multiplied by dA integrated over the area A1, and this evaluated at x plus dx. And what is the force on the other side? Then that is again this term dA, but this time at x. And let's say there is some force delta F yx, right? So we are taking the force because of the presence of the shear stress. There is a force along this direction, so I'm going to take a force minus F yx, just using the same notation here. And this entire thing is now going to be equal to 0, right? Okay, so I hope you are in agreement here. So this implies that my force Fyx, which is by the way the term I am looking for, that is going to be equal to my area A1 plus you have MB. Now this is being evaluated at, I had told you that this at the outer face, now your moment is MB plus dMB because the moment is changing, divided by Iz dA. Right? Okay, and I think I missed a minus sign here. Okay, plus second. So this yeah, right. So the flexure formula, there is a negative sign. Plus again obviously the same integral, but this time only an MB dA Iz, which gives me delta Yx is equal to minus, and you have, so you have a, what is going to come out? So you have this dMB, right? The dMB over this area, so the dMB with respect to the area has nothing to do with that, so I can just take that out. I can take Iz out as well, just small volume, and then you have YdA integrated over A1. And I have made a small error. There's a Y missing here. Please put that. Yeah. Right. Yeah. Okay. So now, if you, I mean, this is all being done over dx. So since this is being done over dx, I can divide. So what I'll do is I'll divide both sides by dx. So I'll put a dx here, and the moment I do a dx here, then this should be dma dx. So this is the derivative of the moment with respect to x. This is going to be the derivative of the force with respect to x on this side, and Iz will just be on as another multiplier, and then you will have this term. Okay. So you already know what I'm going to do. Can you please write it with me? See, this is going to be dyx by dx equal to minus dmb dx multiplied by 1 by Iz multiplied by yda over a1, right? Okay, so this gives me dy fx dx. What is going to be dmb? You have seen this particular term before. Do you remember? And that is that this derivative is now simply going to be my shear force. It's in the negative of shear force. So minus will take care of that. So I will just have plus over here, right? So V by Iz integral y dA a1. And this is a very, very important equation. We'll simplify this a little bit further, but this equation is important. Okay. It just comes from force balance. Obviously, you can imagine that this is going to be related to the shear stress. We don't have it exactly in that particular form yet, but it is. You can almost see that this is going to be related to the shear stress. It is not yet a stress because it's force by a length. If you have one more term here which makes it force by area, you will end up with a shear stress, right? Okay. So this particular term, so what we do is in mechanics, this particular term is also called, so a lot of people call this term, so okay, I'm just going to write this equation just all over again. Okay, wait a second, I'll just copy this. Okay, come on, paste. Okay, good. So this particular term right here, this is also called Qyx, which is also called shear flow. It is not a shear stress. It is the force along the x derivative along the x direction, and it is called shear flow. And this particular integral right here, this is often also called Q. This is the first moment of area often denoted by Q. So we can rewrite the equation as qyx equal to v q iz. See, we are trying to put everything in a similar fashion, right? This equation is reminiscent of the previous equations. Okay, now I had told you that, so this is force by distance. If I can make it force by another distance, q by another distance, I will get the shear stress. So what would be the right here for that? So if we assume that the shear stress, okay, so here what we had not done is, let us say that this particular, okay, let's use a color, okay, let's say this distance right here, this distance is b, okay. If that distance is b, or the width of the beam, then you could divide this. You could divide So by the way, that the circular cross section is sort of a misnomer. It's not necessarily circular. So let's just say it's a constant beam width. If it is, then what you could have done is this tau yx can become q yx divided by b, and this would be v q b by iz. And since tau yx is equal to tau xy, this gives us tau xy equal to vq b times iz. What a beautiful equation. Okay. So this is an important equation. So this is an important equation. Now see, we are going to go back quickly to our naive first cut, that the shear stress was going to be equal to V by A. Oh, I have made a, wait a second. I have unnecessarily complicated our life by using another notation, and we don't want to do that. So this is yx, this was xy. Okay. Right. So we had initially made a naive guess that sigma xy is equal to v by a, and that doesn't appear to be true now, because you have this other very complex formula now, which is v q b into iz. And this quantity q, this actually varies along y. So if q varies along y, so note that q varies along y, which automatically varies along y, which automatically implies that sigma yx varies along y. And what happens at the very edges? At the very edges, q is going to be 0, right? So if q is going to be 0 at the very edges, this here the shear stresses are actually 0. Right? It's actually 0 of, even for the other side. Here it is 0 because y1 is equal to the height, the distance, and there is no area to compute. But here not the same, not true for the other side. But still q will be 0. Can you guess why? Okay? I leave it up to you to figure it out. Okay. That shouldn't be too difficult. The other important takeaway from here is that you can see that in many cases this Q might actually be maximum at the middle, and the stress will actually end up becoming maximum at the middle. Okay, and we will also, you can see later that this initial guess is not totally incorrect. If you say that this is the average stress over this area, this is still the average stress, you will see that is to be correct, but this is not the distribution of stress, shear stress. The shear stress is a function of y, it being 0 here, probably maximum at the middle, but in an average sense it will be v by d. Okay, so the one way to do this properly, or to understand this properly, is we will take a very specific example. So let us take the very specific example of a rectangular. Okay, wait a second, just a second. Before I do this, there is one more final thing I just want to clarify. So this Q, and this will be helpful in some of your results. So this Q is this YdA over this area A1, right, that we had specified. And so this is the first moment of the shaded cross-sectional area with respect to the neutral axis. And hence this entire thing can also be expressed as this A1, area A1 multiplied by y dash star, maybe, where this quantity is the distance from the neutral axis to the centroid of A1. Okay, so distance from neutral axis to centroid of A1, right. Okay, so you can compute Q. You can either do this integral or you can compute it like this also. Okay, so let us now, armed with this, let us now get to let us consider the special case of a rectangular beam. So let us say we have a beam which is such that this distance is b, this distance is h, so my centroid is at b by 2, h by 2. Okay, and you have a shear stress present here, and along this axis you also have bending moment present. By the way, we had assumed that this v does not vary with x, but there is no, later on you can even relax that assumption. Okay. So for this particular case, we can do a couple of things. Okay, but one of the easiest ways of seeing how the stress, if you even come about it from another approach, so you can just apply whatever formula we had applied right now and go ahead and do the integration. You could also, okay, you could also begin with the equilibrium equations. In this particular case, equations. Now the equilibrium equations were discussed in chapter 4, if you remember, and for a two-dimensional case, the equilibrium equations were going to yield del sigma del x dx plus del sigma xy by del y equal to 0, del sigma yy by del y plus del sigma yx by del x is again 0. Right? So we could also begin by applying the equilibrium equations to this particular case of the rectangular beam. I hope at this point you also remember. So this is, by the way, from chapter 4, and I hope you remember what happens if you have if you had to apply the equilibrium conditions in 3 dimensions. So there is another term that will come here. If you had body force term, there's one more term that will come. If you are going to use a circular or spherical cross coordinate system, then these equations will change with respect to that. Okay, so all those are there. Now, in our particular case, this second equation, sigma yy is not there, right? This is just 0. So this forces the other term to be 0 also. So the only equation of interest is this first equation. So let us take that equation, which gives us, okay, so you, by the way, know what sigma xx is. So we say that minus sigma x, this is xy by dy, okay, equal to derivative of sigma xx. Now we do not know what sigma xx is, but we will apply our assumption, which is an engineering assumption, that this sigma xx is given by the flexure formula. So I'll just delete this, and then I will put my flexure formula, which was mb by y by iz, right? And this will give me this is again the derivative. So the derivative of the moment gives me v by iz times y. And now if you need to find out the sigma xy, then all you need to do is just do one integration. So you see what I'm just sort of gaining here is that by using this approach, I have reduced my integration to just a simple one integration. Okay, so if you do this integration properly, then you will have y1 on the other side. This is h by 2 del well, I mean, this is rather straightforward. It's okay if I mean, you should be able to do this mentally, right? I don't have to write so much. I should be able to just simply write y1 h by 2, and on this side you have viz, so you have v y I z. This is the reason I'm keeping this negative and on this side, and c h by 2. What happens to the stress at h by 2? Do you know the value? It is 0, right? Because the upper surface is free of stress. So this automatically becomes my sigma xy evaluated at y1. Okay, and this is v by, okay, sorry, so this I should have done the square. This is a square and there will be a 2 term here. So this is 2iz, and this is h by 2 whole square minus y1 square. Okay, great. So in the regular case, you sort of know that this is being evaluated at y1, so I don't have to write this, but I've still left it so that it's easy for you to understand. This is a parabola. So here the shear stress is going to look like a parabola here with the maximum at the center. Okay. So this is quite an interesting result, and you can, and I'm leaving this as an exercise to you, that you should please verify using the previous form. Okay, and what I mean by previous form is this form, okay, which is sigma xy equal to vq b by iz. Okay, so I'll just write it here, sigma xy equal to vq. Okay, so you can verify it using this method as well. Okay, so this was important result, and one can ask the question, so what is the maximum shear stress for a rectangular beam? And this is something for you to verify that this will actually be equal to 3 by 2 v by a. And I would strongly suggest that you try out these computations in multiple ways. So when you're doing it, you can use this particular formula. You can try to figure out why this is the correct formula using this integration. Try to find out using this method. Also try to see if you can simply use this form right here to guess. See, what is going to happen is that the area is going to be, the stress is going to be maximum for when this A1 is equal to half of the area of the face. Okay, so you have to figure out what this particular distance will be. So this area will be BH by 2. You have to figure out what Y star will be there, Y bar star will be in that case. Okay. I'll leave you with one more result. Okay, and for beams with circular cross section, this result will now become sigma xy max equal to 4 by 3 v by a. Okay, verify yourself. Okay, so we have discussed quite a bit of beams now. The one thing that before I end this particular lecture that I'd like to mention, and that is we made a very important assumption here where we replaced this sigma xx by this form. Now this is a engineering assumption which has to be validated with respect to real life experiments. It turns out that this is a reasonable approximation for beams with thin cross sections. Okay, it is not always valid, and if the beam becomes fatter, etc., in a sense, there are errors that this formula introduces. Yet, this remains a pretty good first cut, even in case of a little bit of a complex situation. This remains a simple method by which you can do an estimate. So these estimates are important because if you are doing numerical simulations, what you will see is that often numerical simulations, if you set it up in the incorrect way, you will end up with disastrous results. And one of the easiest ways to check if the results are making sense is to know and understand these theoretical simplifications, and then you can quickly perform an order of magnitude calculation and see whether the numerical results are making sense at all or not. Okay, so these simplifications are important even in cases where the results actually this simplifications start to break and the results start to become slightly inaccurate. Okay, so I hope I have been able to motivate to you why we have done this, why we have created this oversimplification for a case where we should just be going through very deep numerical simulations, using three-dimensional equations of elasticity and all that. Okay, great. I think I will stop here today, and I hope you've enjoyed the lecture. Once again, uh, I encourage you to go over all the lecture material as soon as I post it. Binge watch it again. That's one of the advantages of me putting this on YouTube, is that you can watch it at whatever point you want. Okay, so good luck. Uh, I will talk to you soon again. Bye.